Well, good morning. Let's see who all we got. Randy, Doug. No, that's my AI note taker there. Yeah, I'm sure we'll have a few more people straggle in here as we get going on things. But maybe I will let it go just a couple of minutes here, just to see if we get a couple more. Say, Bob, do you do Santa Claus this time of year and in your life?
Yeah, pretty much.
Yeah.
The fun part is when I live just north of University Village Shopping Center,
Okay.
and so I often walk down there. And so, like yesterday, I was down there and had lunch at one of the restaurants, and had all kinds of people looking at me strangely. So some of the kids knock on the window and wave and all of that kind of stuff. So it's fun.
So you know what you need a pair of glasses, kind of like mine. You know, the nice round ones like this, and then you kind of
Yeah.
hang them down on the end of your nose like that. Yeah, there you go. There you go. Now you're hitting it. Yep.
I just
Yep.
had cataract surgery, so I don't need the glasses as much anymore.
Oh, good. Good for you. Good for you. How long is that? How long's that been hanging out there? A few years?
Yeah, actually, probably just a few months.
A few
I
months.
went
Oh, good.
in a couple of years ago, yeah, 2 years ago, and
Mhm.
had them checked, and the surgeon said, "Well, you could do it or you couldn't do it. It doesn't really make a lot of difference right now." And so I went
Mhm.
back this summer, and she says, "Yeah, it's time to do it."
It's time.
And
Yeah.
they do one eye at a time.
Okay, I was going to ask about that.
Yeah. And so they did the left eye first, and it was amazing. I look
Wow.
at things, and white trim on houses was actually white. If
Was
I
that
looked at them with my right eye, they looked kind of yellow. So
okay?
that, yeah, it was time to do it.
Okay. Wow. Wow. I've often wondered what the world looks like to people through cataracts. I mean, it's kind of one of those things when you get to be our age, it's just something that kind of starts to creep in there.
Yep, yep.
Yeah, and it's not like it's painful. It's just that it's probably very inconvenient, and your ability to see clearly just seems to be kind of gradually going down. And
Yeah, you see things kind of dimmer,
yeah. Okay.
and at night driving, it's a bit of a problem.
Oh yeah. Sure.
So,
Sure.
yeah.
Yeah. Yeah. Well, and probably because of the gradualness of it, you just adapt. Your brain just kind of gets used to it,
Yep.
and you don't even realize how far down you've gotten until all of a sudden something happens or something you see something and you go, oh, okay, maybe it's time to deal with this.
Yeah,
Yeah.
I started noticing that, particularly, like I said, driving at night was getting to be more of a problem.
Yeah.
And then when I went in this time, she says, "Yeah, your eyes have gotten significantly worse in the last year,
Mm,
so it's time to do it."
yeah.
So
Yeah. Mm,
it's not much of a surgery. I think the whole surgery lasts about 15 minutes.
wow. Wow. That's amazing.
Yeah.
Huh.
We've really
All
come a
right.
long way, haven't we?
Oh, we
Yeah.
have. Yeah, it's
Yeah.
amazing.
Yeah. All right. Well, I think I think we can probably go ahead and get rolling here. And if you if you guys don't mind, those of you that have your cameras off, be nice to see your smiling faces. So tends to be a lot of dark screens with a name on it here, and it's like, okay, y'all, I know who that is, and I know who that is, and I know who that is. I know what you guys look like, but it's like, okay, I'd like to see your faces today. Oh, there he is. Now, Jim, you better turn yours off. No.
That's
Hey, that's
that's
what's
what I was trying to point out is that
uh, hey,
with
that's
the
that's like Santa Claus's brother or something there, you know? Yeah, man,
Yeah.
you probably
this
do a pretty mean Santa Claus, don't you?
this is Santa Claus got drunk last night and hasn't had a chance to which which by the way, I don't drink and I'm 30 plus year 32 years now clean and sober. So
Awesome,
but
awesome.
yeah, no, that's why the camera's off is because people don't need to see that.
Oh no, that's fine. That's fine. That's Hey, Doug, good to see you. Oh, you're muted, by the way. Here, there we go.
I was walking by a mall Santa last Thursday, and he gave me a lot of grief, saying, "We don't need more than one around here."
Yeah,
Can I
yeah.
just say real quick, Bob, your coif and your beard are really impressive. You are
Oh, thank you.
setting the standard to which we all should apply or aspire, and to which I am failing to rise. Right now. That looks good.
We went
Yeah.
down to the Fifth Avenue Theater probably a week ago, and they had their Christmas tree up and a Santa Claus out there taking pictures. And so I showed up with my red turtleneck and my red hat, Santa hat, and he says, "Hey, that's no fair." But we got our picture taken with Santa Claus down there. So
Cool. Cool. All right. Well, let's see. So you guys are all seeing my main screen there. So we'll go ahead and get the meeting rolling here. And of course, as you're all accustomed to here, our typical agenda. And we might be doing some things down the road. That I think. Well, Doug was at the at the Robothon meeting last night, so we were kind of we just sort of touched on the subject of doing some, maybe changing things up some. So we may do some things a little different with the meetings. Um, and there's going to I'm hopeful that I guess I can talk about it, or maybe even you, Doug, you could talk about the Robothon stuff that we talked about that we could pretty much share at this point. But that's when we get to that item in the agenda. But anyway, we're looking at looking at some things to try to kind of drum up more active robotic stuff. Now, James is kind of the exception to that because he's always working on something cool. But a lot of people, it's more time looking and less time actually doing, and it'd be nice to see more people actually building things and doing things. And so anyway, we'll talk a little bit about that later. So I'll go ahead and continue rolling in here. Let's see. Yeah, okay, that's the encoder stuff. Let's see. And of course, we got a resource page and the meetings page where you can go back and you can review anything. And I think we're up to about 3.5 years, something like that, of recordings now. So that's kind of nice. You can go back and review those, watch them again if you want. And I'm continuing to get presenters, and I do enjoy this. We might change this up a little bit and maybe do, rather than having on a regular basis having somebody outside of the SRS coming in and presenting, but having more internal sharing and co-projects and that sort of thing. So we're just kind of tossing ideas around right now as to what that might look like. But in the meantime, though, we'll continue to have presenters come on a regular basis here to via Zoom and share with us. And so if you find you come upon people, or you want to do something yourself, or somebody that's got something cool that they could share, feel free to reach out and to them and invite them to do that, and have them reach out to me, or pass their contact info along to me through the SRS email, and then I'll reach out to them. So, and right now, probably the most active thing is not a lot of traffic on it, unfortunately. Love to see more traffic on the groups.io list. And I don't know, are there people on the relay chat on a regular basis? Anybody? I know. Shoot, now I'm drawing a blank on his name here. He passed away about 2 years ago. Lives out on the peninsula. Amanda and shoot, why am I blanking on his name? Anyway, I know there's some people that like to just sort of plug into that and then just leave it on their computer while they're doing their other projects, and that's certainly an option. But if there is stuff that's going on, that'd be good. That's the one place that you can connect to. We haven't been doing the virtual discussions after the meetings because the meetings have typically been going a little longer than normal. And it's always an option to do that, but a lot of times, I have to run, or maybe, you guys have to get going. So, but that's something we want to do from time to time. We certainly can do that. Don't have to do that after every meeting, but if we get on a subject that's interesting and engaging and we want to keep going, yeah, why not? So you can, get, go to the contact page, and then there's links in there to get subscribed to this list. So, you can hear about stuff. And I think there's a couple of different lists too. There's that, this one's just kind of a general robotics list, but there's other lists for primarily dedicated to announcements, event announcements, and things of that sort. So, I think you can find those, the Robothon stuff. You can find those things over there. So check that out, robothon.org. I haven't checked. I suppose I should check and see how the Makerspaces list page is. I have not. I've not made any updates to that for a while. I have added a couple of new resources. So I usually bold those. So if you're looking down the list there, look at the ones that are bold. Those are relatively new. Not all of them are brand new, but some of them are relatively new. And there's people will sometimes find our list and say, "Hey, could you add this to that?" And I'll go and I'll check the resource, and if it looks good, I go ahead and put it on there. So, and I'm always open to suggestions if you stumble across something that looks like it would be good for that page. And let's see. Of course, the presentations will show up in the calendar view. You'll always see the next coming presentation will automatically come up about, I don't know, it's like 2, 3, 4 days or something after after a meeting, and then you can go into the calendars page, and you can find. You can look at what's scheduled further out, and right now I'm only out to February right now, so I got to kind of get on that and get some more folks out there to March, April, May. So, got any ideas? Feel free to shoot them off to me. And there is a link on the presentations page. There is a link that you could send to people that just kind of talks about our expectations for presenters. Let me I'm going to just quickly bring that up here. And let's see here. I'm going to let's see. Maybe I'll go ahead and drag that over here. Okay, let me get that bigger. And let's see, robots, events, community meetings. Okay. Oh yeah. Okay. So on presenter information here, if you drop into that, it's got a fairly extensive just discussion that I did a while back on what we like and what we're looking for presenters. So this is a place that you could point people to say, hey, well, what are you guys looking for? What kind of a presentation you're looking for? And this just kind of talks through how it works, how our meetings work, where the presentation fits in, and then kind of the general formatting and what we're looking for. And then there's also a link to past presentations that they can go to and kind of see what's been done in the past. So feel free to send that to people, or pass that along to somebody who might be interested and see what they have to say about that. Okay. And of course we got the merch store. I have not. I should probably order something. I'm wearing an old piece of merch here. Let's see if I go. And this was, so some of you guys might remember this shirt from a while back. So this was. Let's see here. Let me do something. There we go. Now you can actually read it. And this is it's a really nice polo shirt. I really like this. I'm assuming that there's probably a polo shirt. Most of these merch sites, a lot of times it's just a t-shirt, just a regular. Hopefully it's a nice t-shirt, good, nice soft material and a good quality material that the image is put onto. But this is an actual polo shirt, and that is a. Yeah, okay. That's not a stitched thing. That's actually like a stencil or something like that on the shirt. But I think there's the only thing on this. I believe it's the only thing on this shirt. I don't think there's anything on the back or anything else. It's just the SRS logo and then the club name on the front there. So, but it's a really nice shirt. I like this shirt. I'm not sure whether I guess I could wear this all the time or wear this now and then when I just go out and about. But get people talking about robots and robotics and that sort of thing. So I will. I should probably do that. Let's see. Okay.
Steve, you thought you needed to do something to reverse the image, but it didn't make a difference. It's always been the right way around. It only reverses for you.
Oh, is that right? Oh, okay. That's good. That's good to know because I don't think I was aware of that.
Yeah, it's a feature so that you can see yourself as if you're in a mirror, right? So that you can move your hands around your face and not get goofed up by it.
Okay. So you're actually seeing it as it properly then.
Yes.
Okay. Well,
as a quick poll, does anybody else, if you turn that feature off, like Steve just did, Steve, do you look weird now to yourself?
Well,
I mean, more than usual.
Oh yeah! My gosh, who is this guy? Yeah, no, I can't. I don't even recognize myself when I'm backwards. So.
Yeah, I think that's really interesting because in the early days of the video conferencing, like a lot of people complained about that.
Sure.
Right? And think about what that means, right? That means that everybody else in the world sees you completely differently than you see yourself.
I see myself.
Isn't that amazing? I love that.
That is, and yeah, if when you think about it, put it in your brain, what you're seeing in a mirror is not what you look like to anybody else, except somebody standing next to you looking at you in the mirror. I mean, if they're looking at you in the mirror, but then presumably you would look different then to them too because of that. But
now, so there's a whole story about people who part their hair on one side or the other, okay, or in the middle, right? And so the point of the matter is you want to get on a video call with just yourself, turn that feature off so you're seeing yourself the way other people see you, and then say, would I buy a car from that guy with his hair parted in that way? Should I comb my hair the other way, right? I don't know if it's true, but there's a story that supposedly people have changed their hairstyles in order to look more correct and have seen a difference. Now, that's goodness knows if that's real or not, but I just think it's
yeah. Well, that's kind of fascinating. I was thinking it'd be funny to have the reverse image. It's like, okay, when I flip reverse, then this happens. So.
Oh yeah. Exactly, and that's the whole thing about like how mirrors work is that's what you're shooting rays through your head in order to see what's on the opposite side. That's what the mirror is actually. I love that. Anyway.
Right. Well, see, I just cut my hair really short so I don't have to part it. Then I don't have to figure that out.
Exactly. Yeah.
By the way, you also sound different from the way people hear you.
Yes. because of the bone conduction, inner ear bone conduction thing. Yeah, it's, oh man, it's like, wow.
Yeah, speaking of hair, when I went into the Navy, I was the only guy in the group that didn't have to get a haircut. Mine was so short to start with.
Yeah.
But you missed out on that whole thing of rubbing your head when all your hair is gone, and how
Yeah.
weird it is.
Yeah, because it was always that way up until that point. I
Yeah.
actually let my hair grow when I went into the Navy.
Mm. Okay, let's see. Yeah, so there's on the front page, left side, kind of upper left side there, there's an information panel, and there's a link to the merch store on there, so you can always easily get there. Or if you've got your phone handy and you want to shoot a picture of this QR code, that'll take you to it as well. And not sure how quickly things come. I believe these I think the store is pretty quick in terms of fulfilling orders, and you can, order one or 100, if you, whatever you want. So let's see. Oh, you know what? Well, that's interesting. Okay, now I gotta. Oh, yeah. I probably it probably would have helped too if I'd actually loaded up the right slideshow here. So let me just. I'm just gonna. Oops. I didn't mean to do that. Sorry. Here, I'm gonna shut these down. Okay. Let's see. I believe there's one more of these next Saturday this year, for the Build It with Arduino with Donna Smith. So if you're inclined to join that, please do. From 1 to 3 p.m. Pacific time, and you could go on the meetup group to find the details, and you can also find links to the past videos that she's recorded, because she records all those sessions, posts them. And you can always reach out to her via the SRS group or the Robothon page if you've got any specific questions about that. Speaking of Robothon, okay, so now we're here at the Robothon page. There's we're looking at, we were having discussions with the let's see, Bob Farrow from Western Allied Robotics, and they're using an old grocery store that has been kind of repurposed by another nonprofit up in downtown Seattle. So it's kind of right up in the middle of downtown Seattle, and not a ton of parking. There's about 24 parking spaces around this place, but it's a physical venue, about 12,000 square feet. And so they've been doing their events up there, and that's something that we could utilize as well. And so we'll be having some more discussions and talking more detail about that. But there's a likelihood that we'll do an event, possibly in conjunction with their events or close to it in that facility up there. So you'll hear more about that via the Robothon website and announcements that'll come out on the list. So I think I'm not certain about a spring event at the field house. Again, this is, things are just kind of getting wrapped up for this year. So we'll see, as as things progress, if we decide to go forward with a couple of events. But let's see, the field house is probably comparable in size to this place. This place is, because it's picture a grocery store, the ceiling heights you got in a grocery store. So it's probably like a warehouse, but not quite as high as ceilings in there. So, but it's a large open space. And so anyway, we'll keep you up to date on that as things develop. So I might possibly roll one of these things into the March slot if I don't find somebody to to do a live presentation. Then we'll have an open discussion, and they are always fun. I have a number of these kind of ready to go in my hip pocket in case a presenter doesn't show up or can't do a presentation at the last moment, that I've got something we can slide in to give us a interesting time anyway. So and if you've anybody that's got any inkling to do leading one of these things, all you need to do really is just kind of pull together maybe some YouTube videos, some information out off of the web, and just facilitate the discussion. So you don't have to be the expert on the topic. Just come up with some good questions that get the discussion going amongst everybody, and we'll all talk. And that's really the goal of these kinds of things, and they're a lot of fun. We haven't actually done one for quite a while, so it might be good to just put one in there and make that a hard commitment, so that we get to do that again. So I'll think about that. So we're going to be here's what's coming here near term. We'll be doing Bob Higgins will be sharing more on computer vision and data processing, and I know he's got some cool stuff to share with us about that. And we've got Craig Austin's going to be talking about his autonomous mower project, which is he's shared that. I think if you were here last month, you saw pictures of his machine, and so we're looking forward to that. And then Lloyd Moore is going to share the presentation that he was going to do in October that didn't happen because of technical difficulties with Zoom. So he will be back to share about choosing the right programming language. So. And of course, all the links and everything else stay the same month to month. And so Bob will be sharing answering that awesome question: are we there yet with visual odometry? So we shall see. By the time he is done, perhaps we will know the answer to the question, or maybe we'll just have more questions. So so stay tuned. Whoops. Oh, there we go. Okay. Now it's your turn. So I'm hopeful that somebody here has something that they would like to share. I'm always open to that, but I do have some interesting, I hope interesting YouTube videos that we can use as just a kind of a jump off point. So I see. I don't see Dick's smiling face there, but he's always had very interesting projects that he's worked on. So, James, you got something cool to show us?
Oh, nothing cool. I just if I can get away with it, I'll drop a link into the class that I'm getting ready to teach for UCSD Extension. New intermediate version of the class. I did the intro class last time around, and now it's the intermediate, which is a little bit higher level. So if it's okay with you guys, I'll toss a link in. It's gratuitous advertisement and misuse of the group, but it's what I do.
Oh, I thank you for mentioning the chat too. I just now saw your note about the Zoom link in the.
Well, there is a Zoom link in the meetup, as far as I can tell, but I don't know whether or not you guys wanted to do that or didn't.
It does refer you to the SRS website, doesn't it? In the meetup?
It does, yes.
In October, for some reason, and I don't know, maybe I did it, maybe my wife uses this from time to time, and my daughter, and somehow or another, all of the SRS meetings got deleted from the schedule, all the future meetings. Well, when you go into Zoom and you set up a recurring meeting, it automatically generates a new link and a new meeting ID. You can either use your own personal, which is I don't do typically. I just said make one for me, and then this is going to be the SRS. That's the one that we've been using probably from the beginning. And then somehow all the future ones got deleted. So I had to go back in there, create a new one. But I realized that you can't set the meeting ID. You can set the passcode, but not the meeting ID. So that's the reason for the new link. And I only want that link really in one place, because if it does change, I want to be able to go to that one place, fix it, and then it's done. You know, I don't have to worry about, oh yeah, change it here, change it there, you know, and make sure that they all agree. So
the one guy who was lost, who posted a message on Meetup saying, you know, hey, the link ID is bad. I said, hey, go and check the actual main website.
Yeah,
and that link is correct.
Yeah, I that's interesting. Yeah, I've often kind of wondered how many people hit the Meetup looking for us. It'd probably be good. Maybe it would be good to go and kind of revisit that and make sure that that does a good job of getting people over to our website so that they can actually find us. Because I hate for people to get lost, you know, or frustrated trying to get to one of these meetings, because it's like, it's not hard to do this. If you know to go to the SRS website, it's right there. And then, you
Right
know,
there, yeah.
there's
But, you know, we should try to find out how many people aren't able to find the meeting. So everyone who couldn't find the meeting, could you please raise your hand?
Okay.
And
Everybody who's not here, please raise your hand.
all those bombers who came back with bullet holes in one area, that's where we need to reinforce. That's a famous version of that one. Anyway.
Oh yeah.
So Steve, by the way, that what do you call it? A document that you showed us that we should refer potential presenters to. It had a link in it, and I don't know if it's the old one or the new one.
The link in there. Okay, as I recall, I think I did I deactivate it? Deactivate it? I had the. It's not an actual link, is it? I mean, like
It looks like one.
It looks like one, but you can't click on it.
Oh, okay.
It doesn't do anything when you click on it. I thought I'd actually remove that, because or just send something that goes to the main page. I don't want to have that link in multiple places on the website, because then I have to remember to fix them. You know, I hate it when when you got to do stuff like that. You know, it's like. And those are the kinds of things that usually bite me in the butt too. You know, it's just like, okay, I mean, I thought I got everything done. Oh no, missed it, missed one. Okay.
The smartest people know how dumb they are.
Oh yeah, and yep. And the older you get, you know, the more the realization dawns on you. You know, it's like, yeah. When you were I remember when I was, you know, teenager. I mean, I was like, man, I knew everything. I was the smartest guy on the planet. And then you get into your early 20s and you're a little bit less than that, but not much. No, that's still pretty high at that point. You start getting into you get married, and then you start having kids, and you realize how lost and completely clueless you are. And then you get older and older, and your kids grow up, and it's like, holy mackerel, how did they survive me?
This is the quote I love is, I left the house at 18. I came back home at 22, and it was amazing how much the old man had learned in 4 years.
Yeah, that's yeah, it does kind of seems that way, doesn't it? I don't remember really ever feeling that way about my parents, but it was definitely I probably thought I knew more than I did, or understood more than I did. And then, when you get out there in the real world and you have to start facing things on your own, you don't have other people bailing you out. You realize pretty quickly, how smart you really are or not. So any of you guys so shall I go ahead and pull up a YouTube video here? Let's see here. I got to get this guy. Okay. Pause that for a sec. Got to make sure that I get this. I don't have the sound sharing, so I'm going to make sure I do that here. Share screen. System audio. And
haven't got that set up yet. We're just doing basic stuff. I know it does, but it catches itself.
Ground on the ground, it's just all kind of stuff.
There's no distinction. There's no distinction.
All right.
Thought it was interesting how they made his head so incredibly empty.
I was thinking the same thing.
Just matching humanity.
Right. You ever watched movies where like I don't remember which movie it was, but I saw one recently. It was like a clip from it, and the robots were there was people were going out and they would shoot the robot in the head to kill it. You know, like in a I mean, you want to kill a person. That's a pretty good place to do it. You know, shoot them in the head. They don't survive. But shooting a robot in the head may have no effect at all, because where's the brains of the robot actually located? It could be in their ass for all you know. So maybe you got to turn around and shoot them down there. I don't know. It's like, how do you pretty much have to fill that robot full of lead and hope you hit the right spot, right?
I think that isn't the spot that's going to take the one thing that's going to take everything out, that's going to be the largest physical size in a mobile robot like that. It's got to be the battery, right?
Yeah, sure.
I would imagine so. Center mass, look for the, maybe low center torso. I mean, if I were designing a mobile or a walking robot, that's where I'd put the battery by and large, keep the mass low and center body. So that's probably where it is. So really what you want to do with robots is shoot them in the nuts. Sorry.
Actually, what I've seen in the Tesla robot is the battery is in the back.
Mm-hmm. You could imagine a robot built for, like, say, military application or to be a policeman or something like that. You could have a distributed brain, right? Connected via Ethernet all through its body, so that you'd have to do a lot of shooting to take him out.
I suppose you could have distributed batteries too, right? I mean, there's no reason why you couldn't.
Oh,
Just distribute the cells all over the place. So you could, take out an arm or something, but the other arm and the two legs still work, or take out a leg and it keeps hopping, or, whatever.
Now,
it's a rough problem.
I was thinking that if you've got a regular biped, you might actually want the weight to be high. You might actually put the battery in the head, because you want an inverted pendulum that you can, count on.
You're absolutely right, Doug. Yeah, that makes perfect sense.
Yeah, makes the balance.
As a matter of fact, an acquaintance of mine is actually building a little balancing robot, and people keep suggesting to him, well, you just need to put a boom and then put a weight up higher so that it can balance easier. And he's like, no, that's the easy way out. I'm going to get this control loop and the sensors, and he's building his own accelerometers so that it can be really tiny and still balance.
Well, okay.
What's always amazed me about some of these robots is just the motors. If you go out and try and buy a motor like that, even if you could, they're thousands of dollars.
Oh.
It's just absolutely amazing.
Yeah.
You're saying that the amazing part is the cost of it? Yeah.
Yeah, and the size. For the amount of power, yeah.
Well, so they're using not necessarily BLDC motors. I think a lot of them do use BLDC motors, but also these what are they called? Hoverboard motors, right? They're sort of like halfway between a BLDC and a uh, and a like a stepper motor, right? So they have like they only have 3 coils, but they'll cog to like
Yeah. Yeah.
12 positions or something like that, right?
Yeah. Yeah. Yeah.
And I think that the power density between those and standard DC, old school DC permanent magnet motors isn't that big. I may be wrong about that, but the last time I remember looking at it, your standard old DC drill motor is pretty close in power density to those motors, but nobody wants to use a DC motor, I guess, because of the noisiness and because they wear out. You know, maybe they're not as efficient. I don't really understand what the deal is with that, but I've built some cool stuff with nasty old DC motors that I pulled out of dead treadmills, you know, for free. So I'd love to see it, you know, like why aren't we building these walking robots, guys? We need to level up. Yeah, right.
Yeah, I've been working on arms, and the first arm I did, I thought some pretty decent motors in there, but boy, I'll tell you, by the time you factor in the mass of the arm itself and the other motors that are out there on the end of it, uh, you got to have some really big motors.
And were you using like servos? Because those are almost always DC motors inside.
Oh, I've used in parts of it servos and BLDC motors and things like that. Yeah. Um, so for the shoulder, I just use some garage door opener motors, and they're pretty strong.
Nice. Yeah. What was the other one? Somebody I saw built a robot with a the motor that raises and lowers the window in the car.
Oh, yeah. They're pretty good size also.
Yeah, the only problem with that was the gearing had horrible backlash, but because he just wanted the whole gear train and the motor and the whole thing. So he wasn't just using the motor, he was using the whole thing, and the backlash was horrific. But you know what he did? He was using it for a lift, for basically for joint 2, the lift joint on the arm.
Okay.
And he said, you know what? I don't care about the backlash because it's always going to rest on the bottom side. It's always lifting something, right? And as long as I move slowly and I don't jerk it, the backlash doesn't matter. It's pre-sprung because of the weight of the arm is always going to be this way.
It's going to be hanging there. Well, actually, that's pretty smart. As long as you follow the basic rules. Yeah.
It makes a difference though if you have an arm outstretched and you want to turn it over, and now all of a sudden it gets to that point and it flops.
Yeah,
because of the backlash. Yeah,
exactly. Yeah, you can't go up and over and then
yeah.
So yeah,
but you know this is the thing is I think everybody, a lot of actually let me ask the group. Maybe this is a good suggestion. The robot arm that everybody loves right now, and I'm going to forget the name of it now. It's a something 100, and it's an absolute pile of garbage. I should look it up really quick. Maybe I will in a minute. But it's basically just a set of servos all stuck together, right? And they're all pretty nominal RC servos. And if you watch this thing move, you know, it's like it's jerky and it's wiggling and there's no counterbalancing, so it's weak, and the shoulder servo has to be huge, and it's a pretty small arm. But it's the one that a lot of the people who are doing the AI training of robotic arms are using. And so everybody's like, oh, that's the one that'll work. That's the one I want to build. So I have kids coming to me and saying like, hey, Professor James, which robot arm should I build? This one looks like a good one. Should I build this one? And it just kills me to say yes, because it's such a pile of garbage, right?
Yeah.
But at the same time, I understand, you know, most are like, well, do you want to learn about how robotic arms, or do you want to learn about how to train robotic arms? Like, are you interested in the controls? But I was looking around to see if there were any other good examples. And I you know, if anybody has links to like good designs of easy to make or off-the-shelf purchasable robotic arms that aren't insanely expensive, I would love to get the link for that. So
Yeah. Is that I found this thing called SoArm, Standard Open Arm 100. Is that it?
that's the one. That's the one.
Okay.
Yeah.
Okay.
Yeah.
So yeah. So if you let's see here if I can get a. Oh
And
well, I'll
and if
just.
you just look at like videos of it moving, I mean, it's utterly horrific. Uh, and it's super weak. It can barely lift itself, much less lift anything else. I mean, the typical
Yeah.
demo for it is like folding laundry or something, and so it, like it's strong enough that it can lift up the laundry and stuff, but that's about the end of it.
Yeah. Okay. So yeah. Yeah. So. So dash. Yeah, I'll try the so dash arm dash 100. See if that helps.
But there doesn't seem to be really anything else available. So
Yeah.
Bob, hurry up and get your design done, publish the files, and then we'll all build one.
Well, the first one didn't work that well, so no
No
takers.
promises.
But
Well,
hopefully I'll get the second one working a little better.
and I mean the Dexter arms are great, but they're so complicated and so expensive, and there's so many moving parts in the dang thing, and the control system is so FPGA constrained that the barriers to entry are just off the chart. So
Off the chart, sure.
It's not worth worrying about anymore.
Yeah, yeah. When I just kind of did the general Google search, it popped up this SoArm, and then it also popped up Universal Robotics UR3E for $33,000, and in the UR12E for $44,600. So it's like,
but everybody's going to have one of these in their home, and it's going to take care of you. And poor people won't have to work anymore because they'll have a robot.
Right, yeah. Well,
but the price there gives you an idea of how complex and how hard it is to actually build one of these things. So,
oh, sure. Yep. Okay. Well, it's fun to watch the robots like that one in the video with you, the robot has the ability to sort of spin the arms all the way around, so the thing can be laying flat on its back. It can rotate its arms in such a way that it can just lift itself up off of the ground or the floor and back up into a vertical position. Would be kind of handy if we could do stuff like that. Because you get to be our age and you're like, maybe playing with the grandkids on the floor, and it's like, can somebody help me get back up? Because it's like my arms won't move the way they need to move to get me, get under me so I can lift myself back up again.
yeah, so the first version of the arm that I built just had kind of human type motions, so it couldn't do that. But this next one's going to have slip rings so that the arms can go all the way around. Why restrict ourselves?
Yeah, exactly. Let's see. Well, there. Let me. I'm going to show you. I got one more video here about and maybe some of you have seen this Lego powered submarine. So it's a kind of a really quick guy building a Lego submarine with a compressive cylinder in it, and it's fun to watch because I love Lego construction stuff. So I mean it's always cool. So let me.
I love his power transfer for the propellers with the magnets.
Yeah,
it's really good.
Okay, so let me. All right, so now let's see if I can make this thing bigger. Oops, let's see. Building Legos. Okay, so let me get to the share screen here. You know what? I'm gonna leave the sound off on the thing because really all it is just the machine, the motors running and stuff, and that way we can kind of talk about it as he's doing it.
Oh, this is even a different one, I think, from the one
It's
that
a
I've.
different one than using. Yeah.
Yeah, because the one that I saw, the guy used a. Oh no, I have seen this one too. But there's another one where the guy uses a like a plastic tote kind of a thing. One of those like it's like a food saver container, and he locks the lid down on it. But yeah, this is great.
I mean, it is just fun. I mean, the Legos are such an amazing, wonderful toy and tool, and the kinds of stuff that that he does with it. And
It's also cool that he has enough torque out of that actuator to move that plunger in and out. I did a whole thing with a reagent robot years ago, and finding a plunger that didn't stick too much was actually pretty hard. We ended up with a glass one as opposed to the plastic. So yeah, good job on that.
How did he? So how did he? When he had the thing in the swimming pool, how was it? How was he controlling it?
Well, he mentions an RC receiver in the video here.
In the
I saw
video,
that
okay.
So, but yeah, I do have a question about that because one of my other jobs was doing a data logging inside of cows' stomachs, and a cow is. I spent a lot of time with my arms in a 55-gallon drum of water trying to figure out how to get RF to go in and out of water. And you could do it, but the range is just horrific. So
yeah,
he must be holding the transmitter just like right above the surface of the water or something, or he has a really strong RC controller. I don't know.
yeah, because penetration of radio waves. I mean, like high frequency radio through water is very, very small. Yeah.
Yeah, so the Navy uses VLF down around 18 kilohertz.
Okay.
Yeah.
But they have big, monstrous 2 megawatt transmitters too.
Yeah, it takes a lot of power and very low frequency and data bandwidth. And so he's obviously not using that.
And I think in that case, Bob, isn't it the case that you have to have a really long antenna?
Yep.
So
yeah.
So the subs end up streaming out a wire behind the craft.
Right.
Yeah, it goes out quite a little ways. Yeah,
yeah. And the data rate is really low
coming out of this at all. I mean, it's very much just there.
And
I love the. Did you notice, guys, that he has a gear train as well on the propeller, and so that the magnetic coupling, I guess, doesn't have to rotate at the same speed as the actual motor shaft.
Oh, sure.
I'm not sure. I don't know if that actually makes a difference, but I just thought it was kind of interesting.
Yeah.
And also how he did that magnetic coupling. I wouldn't think that it would be that strong, but I guess it doesn't really, maybe it doesn't need to be all of that strong. I mean, it's just pushing against water, and as long as you don't go too fast.
Yeah.
You're okay. Oh, he has 2 motors, doesn't he?
Yeah.
He has 2 motors and 2 magnetic couplings. Oh, but they're driving 2 different propellers. One of them is driving, or are they driving 2 different propellers?
Let's see. Okay, now, yeah.
So if you take the magnets out of an old disk drive, hard disk drive, those are really strong magnets.
Yeah. Okay. Yeah. So he's got 2 because he's got one going off to the left.
Yeah.
And then one go. Okay. So what he should do is a differential drive, because then both couplings will drive both motors, which is good.
Okay.
A lot of people see that.
But I just noticed he's actually geared up.
Yeah. Yeah.
I would think you'd want to go the other way, but because that means his magnets are that strong that he can
gear. Yeah. See, this is a great video, and I love this. Maybe somewhere there's a longer video of all the stuff that he tried that didn't work before he got. That's the video that I want to watch, right?
Yes,
like that didn't
absolutely.
work. Those are the ones I really enjoy.
Right. Yeah, it's right. Did you guys see the article about the? It was one of those. I think it was an Argo. The robots that they send them out. They just drop them in the ocean and they sit there and they descend and they take salinity and temperature data, and then pop up and send it. I think via satellite, ships the data home, and then it does its thing again. And it just sits there and it does this up. The submerged surface cycle thing. Over and over and over again. And there was one that got stuck under the South Pole for like 8 months. It was under the pole for the whole time. And they'd never purposely sent one of these things on that kind of a mission before. So when this thing popped up, it surprised them that it was like they thought they'd lost it because they hadn't heard from it for 8 months. And all of a sudden this thing somehow got dislodged and got itself back up to the surface and started sending data. And they found that this thing had gathered data that they had never seen before. The kind of data that they had, and was kind of amazing. And of course, the fact that this machine was able to continue to function, the electronics and everything else worked for all that time without any anything coming in from the outside, no retrieving it, plug it, swap out the battery or plug it into a charger or whatever it is they do when they're out there servicing these things. And so it's kind of a serendipitous. It was able to gather this data. They probably after it came back, it was like maybe we should have done that before, but they had no idea whether one of these machines would survive that kind of a mission. Well, apparently they're pretty well built, I guess. So
that's actually one of my favorite areas is stories about machines that survive when they shouldn't. So there's a YouTube channel for a guy who goes out and finds old cars that are rusted in a field, and then he's like, will it crank? I think is the title of all of his videos. So it's like this ancient car, and he manages to get them running again and drives them off, with the wood frame and the wheels rotting and all that kind of stuff. There was a satellite not too long ago that had been put up, and the battery had failed in it eventually. But then eventually the connections on the battery corroded to the point where they disconnected. And then when the solar panels were in the sun, the satellite would wake up and start responding again, which I love. And then there's the Philip K. Dick. No, it wasn't Philip K. Dick. It was the other guy. Harlan Ellison, I think, wrote a story about a satellite that wakes up in space long after humanity has wiped itself off the face of the earth and communicates with a set of entertainment robots on the ground, which are a gigantic Mickey Mouse, Goofy, and Pluto robots, which then I think inspired this recent movie where they had these massive entertainment robots that were a part of some war or something. I haven't seen the film. And then there's the book series Bolo, Tales from the Dichromatic Brigade, which is all about robotic tanks. It's got the development from like security bots up to planet-ending, super intelligent, hyper intelligent robots that supposedly serve humanity. So obviously science fiction, but
yes,
fun stuff.
Okay. Well, does anybody need a potty break or anything here? I could use one, but so if we want to just how about 5 minutes? How's that sound? So I've got right up on 11 o'clock your time. So how about 11:05? We will reconvene here, and I'll just share the. Let's see here. Where are you? There we are. I will share that screen. I don't have a clock on it, but I'm sure you guys can tell time. So we will be back in about 5 minutes and get Bob rolling on his presentation.
So looking forward to this, Bob. This is going to be great fun.
Yeah, that doesn't make sense.
Going again. Okay, recording is starting again. Well, thank you, Bob, for putting the presentation together for us here. And I know James has definitely been chomping at the bit for you to do this, so we are looking forward to it. I won't babble on anymore here. I'll just let you take control and go for it.
All right.
And let's see. I will stop sharing. There we go. Okay.
Okay, so how do I take control here?
So you should be able to, down the bottom of your Zoom screen, the green square there that says share screen, and then
Yep. Okay, so how's that?
let's see. We're not seeing anything yet. Let's see. Did
Oh,
you? We're seeing you.
okay, just a minute here.
Yeah.
Okay, that's the one.
Okay.
Is that better?
That is okay. So just go ahead and hit what is it? Presenter. Yeah, slideshow. Yeah, looks good. All right.
Okay, so I put together some stuff on visual odometry, which is basically using the cameras to tell how far you've moved. Kind of like the wheel odometry, but when the wheels spin, they don't work too well for odometry. So if you're looking out at a scene, you can use the difference in the view to determine how far you've gone and how much you've rotated.
Sure.
And so let's see if I can play this. We'll change here. All right. Since I can't see, can you see that, the picture of the ground with the blue circle on it?
Yeah, it looks like it's a video.
Yeah.
Yeah.
Okay. So this is somebody's visual odometry system, and you can see the blue track going around the circle, and the upper two scenes are the 3D camera, so left and right image of the track that he's taking. So it gives you an idea of what you can do with visual odometry. So he can plot his track and knows exactly how far he's gone and what his angle of rotation is relative to the scene.
Mm-hmm.
And you can see him now take off and go down the other street.
And this is not slam. Like, he's not updating the world map from
No,
this. He's
no.
just like
He's
his
just tracking
track
his.
is so accurate that he can actually just.
Yes.
Okay. Cool.
Okay. So that's kind of an example of what you can do. This is the one I want. Okay. So get back to the slideshow. Okay. All right. So what is visual odometry? So typically we put wheel encoders on a robot to estimate how far he's moved and what direction he's turned and the rest of that. And the problem is that sometimes the wheels spin on very smooth surfaces, and so the estimation of the robot motion from the wheels is not real good. So visual odometry estimates the motion of the robot by estimating the change in pose of two different camera images. So as you can see over here, you're on the left side there, you're looking at a point and it shows up in one image. And from the right, you're looking at the point with the translation and rotation, and it shows up at a different point in the image. And so knowing where it shows up on those two images and having a well-calibrated 3D camera, you can actually determine how far you've gone. Okay, so the difficulty is one of the same things that you have with wheel encoders, in that any errors that you have on one short segment are going to accumulate as the distances get longer. And so you're going to accumulate errors. And the same is true over the visual odometry to some extent. To some extent, you can actually improve on that. And I'm not going to talk a lot about that, but just don't have time. Okay, so why use it? Not affected by wheel slip, GPS outage. So if you can use it indoors, or several of the other issues that you might have from odometry systems. It can provide more accurate estimate of position than you can achieve with the wheel odometry alone. And if you're smart, you can actually put the two together with some sensor fusion and get some really good odometry. Or use inertial sensors or some other sensors along with the visual odometry. And sometimes that can correct a lot of the errors. By the way, if you have any questions, just holler at the time. That'll make it easier for me to figure out what's going on.
Okay.
Okay, so what do you need to do visual odometry? Okay. So one or more cameras to collect images. So you can do it with a single monocular camera, but there's some difficulties with that. Or you can use a 3D camera. So what I've got here is basically for a 3D camera. Okay, so you need a computer to process the images and align them to estimate the motion between the times of the different image captures. Okay, that's it.
I feel like you might have left out a step there in the processing part.
Okay, so you want to know what kind of camera to use. So we've got different choices. How do you process the images?
Mm-hmm.
What kind of performance can you expect? Well, I think you saw the initial video there that performance can be pretty good, but it depends on a few things that you have to do. So, what factors really affect the performance? Is it computation, or is it the images, or what? Okay, so here's the process. You grab a sequence of images, you do what's called feature detection. So, you find some interesting points in those images, which you can count on being there. You do that for the first image, you do that for the second image, then you match the features between the two images so you know it's the same feature that you're looking at. Then you do the motion estimation computation, and then there's this optional thing which is called bundle adjustment. Don't have enough time to talk about that, but what it allows you to do is take multiple images and treat them as one, and so improve your error, basically, reduce the amount of error that you have. Okay, so basic visual odometry system types. So there's three, which is a 2D to 2D. So this is the monocular camera, but the results are only valid up to a scale factor. So you have to have some sort of scale factor must be supplied separately. And so if you have something in the image sequence that you know the size of and you know how far away it is, uh, well, I can't say know how far. If you know something that you know the size of in the images, then you can get your scale factor and get an actual distance.
Mm-hmm.
3D to 3D, so a stereo camera. So you match 3D point correspondences in the two images. Some potentially larger errors in the depth estimation because of the way the 3D cameras work. But it's a pretty good system. Okay, 3D to 2D. So you start out with a 3D camera and then use a 2D result in the second camera. Minimizes the reprojection error and potentially, and I'll underline that, potentially you can get better results. I've not built this one. I've built the 3D to 3D, and that's what we're going to look at for the rest of this.
Hey, Bob, on
Yeah.
the 2D to 2D, the some sort of scale factor, would that be like an April tag? Would that be an example of that? Or like what does that mean?
Basically, it has to be a scale factor in the image. So if you have like a box that you know the dimensions of that appears in the image.
Okay. So an April tag would be a box that I know the dimensions of, and then I would be able to figure it out from there. Or I guess it could be like if you see a human being in the image and you know roughly how big a human being is that the sort of thing?
Yes. Yeah.
Together? Okay.
Yeah. Yeah.
Cool. And then on the 3D to 2D version of it, so you're not going to talk about how you maybe it'll be obvious if I shut up and let you continue on.
I don't plan to really talk about the 3D to 2D. If you want, I can come back and look at that at a later time. I didn't get as far into this whole presentation as I wanted to because I wanted to do this, but just too much there to do.
I hear you. All right. So Steve, just start expecting requests from me for.
Okay. All right.
But what you'll find is that if you have a stereo camera, the 3D to 3D works quite well. Okay, so the sensors, cameras. So you can go out and buy a stereo camera, which has the two imagers, and you will have larger error at longer range. And so this kind of gives you an idea over here on the picture. The range that you get, or yeah. So the amount of range that you get, it depends very much on how far things are away. And so slight errors in the displacement between the two images is going to give you a large range error. So any noise in this gives you large range error at long ranges. So one of the things that people do is when they're doing the computations, they weight the computations based on the range. And so long range images or long range points, they don't weight as heavily because they have a larger error. Okay. Potentially another thing you could do is with a LiDAR. Okay, so now you're getting really good range estimation. Unfortunately, there's no way to match the points. So if you have a LiDAR that's associated with some kind of camera where you can actually match the points, then maybe you can get better performance. And you might even be able to find some other 3D sensors, but okay. So here's what the image processing really looks like. So we talked about image sequence. So we'll talk about feature detection, feature matching, and the motion estimation, which is computing what's called the essential matrix and then extracting rotation and translation from the essential matrix. And then you concatenate the poses to actually get your track. And so it's actually fairly simple. But first, there's always a but first, isn't there?
Mhm.
So there's a lot of things that you need to do for image prep to get good images so that you can actually find good points and match them. So you convert the image to monochrome, and then you use do some kind of undistortion. Any camera you have is going to have some distortion due to the lens. And so you have to take that out and use the camera calibration coefficients that you got from the 3D camera to take out the distortion due to the lenses. And then that gives you what in effect is a pinhole camera view. And the image is actually linear rather than distorted. Okay, noise removal. So shot noise, something like a median filter or what is called a bilateral filter. And then you have Gaussian noise. Okay, which one do you need? Just like everything else, it depends. So if you're in a very noisy environment, i.e. your camera or your cables are not well shielded and they go by a motor, a DC motor that's a PWM driven, there's going to be a lot of noise, and some of it's going to be the effect of shot noise, and so you're just going to see spikes along the image. Gaussian noise, just random noise, easy filter to build. The other thing you do, and this is actually quite important, is to normalize the image so that it has the same mean and variance. So if there are lighting differences between the images, those are taken out. And then you need to do some stereo processing depending on the camera. Okay, so to convert to monochrome, very simple. And here's the formula. It's not complete agreement across the industry about the coefficients. They vary a little bit depending on who you're talking to. I think these are the ones that are used by OpenCV. Okay, so here's your OpenCV statement that converts it from a raw image color to gray image. Okay. You have to watch out here for the color. Depends on the order of the channels. So blue, green, red. There's also RGB and others. There's a dozen different variations here that you can use. So why do you want to convert to monochrome? You got more information in the color, but the additional information you get from the color channels is almost useless. You're better off just to go to the monochrome and do the simple one-channel processing. Noise removal, all kinds of different filters. I mean, hundreds of different filters. So this was kind of what I used for several of the filters. So no filter, just copy the image. Gaussian blur, and you can set the size. This is a 3x3, and I chose several different sizes that are in here in the middle. Median filter, very simple. So this is size 7. 7x7 box. And a median filter is different than the Gaussian filter. The Gaussian filter basically takes a weighted average of the pixels around the center. The median filter rank orders the values of the pixels and then picks the one that's in the center of the ordering. So it's more likely to take out shot noise. Bilateral filter actually does pretty good on both. It's a little more complex filter, and so it takes a little longer to run. So whether or not which filter you choose depends on what kind of noise you have and how much time you have between frames.
So just a quick question on that. In every one of those cases, oh, you're going to go over that right now. You're losing, I mean, it looks like you're losing resolution, but you're really not.
You're not losing resolution, so you still have the same resolution, but you're adding blur. So yeah, yeah, you can kind of call it losing resolution, but like I said, it's not really loss of resolution. You still have the same number of pixels. It's just a blurrier picture. So this first one is a relative close-up with no filter. And so this was part of that initial picture that you saw. And you can see even it has a little blur on it, and that's because it's a fixed focus camera. And so, yeah, you can expect some amount of blur. This is a 3x3, so you can see a little bit more blur added. This is a 5x5, even more blur, and a 7x7, and it's even more blur. So finding crisp points that you can say this is the image point, like maybe you want to find a point right here as being a point that you'll be able to recognize in the next image. And as you go down more blur, yes, you get rid of more noise, but finding exactly where that point is becomes a little bit more difficult. Okay, so here's the Gauss 7x7, which was the last one there. This is a median 7x7, and it's actually pretty badly blurred around the corners and the edges, so it's probably not something you want to use. This is the bilateral filter, which actually takes out the Gaussian noise and the shot noise. So it's a very good filter to use. But again, it depends on how much time you have. All right. So normalizing an image, very straightforward. You convert all images to a common mean and standard deviation. So you take the image, you subtract the mean of the image off of every pixel, and then you multiply by the ratio of the standard deviations, the one that you want new and what the old one was. And then you add back in the mean. And you go from this to this. And you can actually make it look very much like this just by picking the new mean that you want and the new standard deviation you want. But again, the advantage of this is that all of the pictures will look very much the same. And so it's much easier to match the points that your feature points. Okay, now we've done some conditioning on the image and we can actually work with them. Stereo processing. Okay, so what happens here depends on what kind of a camera you have. And I think I'm missing a slide in here. Oh, well, all right. Ah, no, I guess I'm not. So if you have a stereo camera that you bought off the shelf, it probably does some of the stereo processing internally, and you just load the depth image. Okay. So some of the structured light cameras, like the um, what's the brand name? The Intel cameras. They have a relatively short range, but they do the stereo processing. All you have to do is download the image.
Real sense?
Yeah, RealSense. Thank you. Okay. Sometimes a stereo camera may just come with the software, and so you just call that stereo routine. And I've had one that worked like that. They give you all the distortion coefficients and all of the rectification for the stereo image. And so all you do is just call those routines. Sometimes you may have a stereo camera which only has the camera calibration coefficients, and you have to build the stereo software. Um, and so I have actually done that because I built myself a stereo camera out of a couple of webcams. And actually, it works not too bad. So you do the camera calibration, and then you have to build the stereo software. Okay. So you start with an image pair, you undistort the images and rectify them. That means using the calibration camera so that they look pretty much the same. And you compute the disparity, and this is basically the pixel difference between matched points. And from that, you can compute the range. Okay. Undistort. So we did this in the last episode. So use the camera calibration coefficients to undistort the image. Depending on the sensor, again, you may not have to do this explicitly. It may be done for you. Depth cameras have to undistort the image in order to obtain depth information. But this is what the image may actually look like. And as you can see, it's not particularly linear. And what you want is a linear image so that you can actually figure out what the range is. And so this is the corrected image. It's a relatively simple process. So here are some of the distortion coefficients that you have to worry about. The biggest one, as you saw from the other, is the radial distortion. As you get farther away, the pixel distances change. Tangential distortion is another distortion set of coefficients that people have to worry about. Okay.
But the radial distortion is the big one, right? Usually the tangential is smaller, or
Yes.
yeah,
Yes,
okay.
absolutely. Yeah. So
But
you can see
so
the
tell me
radial
all the
distortion
ones that
here.
you can get away with not doing the tangential sometimes.
Yeah. Your stereo results are not going to be as good.
Okay.
And since the stereo results are not as good, your matching later on is not as good. And so you're going to get error in your estimation of the rotation and translation. So you want it as good as you can get it. So in the distortion coefficients, you see sixth order here, right? And I've seen people carry it out to 10 just because they want very, very good distortion correction. Okay, so this is the original monochrome image, and this is the undistorted image. Um, Pretty much the same, except for you'll notice some of the sizes are changed because the center pixel distances are larger than the radial pixel differences here. And so some of the images cut off. Like over here, you can see this section does not appear. Okay. And that's typical. By the way, I should say that this is a picture of my very messy shop. There's a 3D printer in here. This is part of an arm, and the cupboard's back here. Okay, anyway. So here you can call these CV, OpenCV functions, init undistort rectify map. Okay, so this basically creates a map or two for the X and Y coefficients. Okay, so you got one map for the one image, you got another map for the next image. And then you can use a remap, take the gray image, you compute a rectified image using the two maps that you had, and interpolation, linear interpolation. That's probably what you want because you want a linear image. You can put a number of different things in here. But OpenCV has done the hard work for you. They've written all of the programs to do it. Okay, so then you end up with a pair of rectified images. Okay, the advantage, so this is the left image and here's the right image. And as you would expect, you can't see some of the far things in the left image in the right image, and vice versa. So you can not see some of this over here, over here, whereas you can see it over on the right-hand side. Okay. And that's what you would expect from a pair of cameras that are facing exactly the same direction. One can't see as far to the left, and the other one can't see as far to the right. So basically, the image you have to work with with the stereo is somewhat smaller than what you started with.
But you're making the assumption here that the vertically that's not the case, right? Like you can see everything vertically, or is that not?
No. Well, yes, because the cameras here are separated horizontally. So you can build a stereo system where the cameras are separated vertically, and then you have the problem in the vertical direction rather than the horizontal direction.
Right. But is it true that if they're separated horizontally, then you do not have the problem in the vertical direction? Is that fair to say?
Generally, that's true.
Okay. I was
If
just
they
looking
were,
at that red line, and it looks like it like matches all the way across. So
yeah. So that was the next point, is you can see where the red line is, and yes, it matches very nicely. And so when you're trying to find a point here and find it in the next image, because it's not going to be in the same position, X, Y, all you have to do is search along that x-axis. You don't have to search the entire image to find it. So that's the advantage of having a calibrated stereo camera and the image is rectified. The search problem is not as difficult. And that depends on how well your camera calibration is. Yes. Anyway, so after you do the rectification, the two images are aligned, like you were just talking about. So you pick a point in the left image and match it to a point in the right image. Okay. So you're basically sliding across that line and trying to find out where it is. So if the calibration is good, the point in the right image will just be on the same line, just displaced. And so that's called the disparity, is how far displaced is it? And that disparity or displacement is what gives you your range information. So you just search, do a correlation search along the row to find your match. Okay, I think I just said that. All right. So the disparity is basically the difference in location along that line where the 2 points match. Okay. So you don't have to really do a lot of software here. So OpenCV gives you two functions, stereo block match, left image, right image, disparity. Okay. There's also what's called a SGBM, semi-global block matching. And so you can kind of get a guess as to what that is. So there's a whole bunch of factors that you have to set up uh, before you call these so that it has some idea what it's doing. So one is the number of disparities. How far along the line do you search? And this is times 16. The way they've done it, you give it the smaller number and it automatically multiplies it by 16 when it does it. So the
hey Bob, just to ask here, are all of these things that you're talking about in that int list, are those all part of this disp structure? Is that what's
no,
happening? Or no.
no,
How is that? How is that information? Are you like presetting these parameters? How are those
yes.
getting into the? Oh, okay, all right.
So you call the stereo set uh, number of disparities or set block size or
Got it.
okay. So
Okay,
there's a separate
thank you.
call function for each one of those. Um, and that's so that you don't have to pass them across to the stereo algorithm each time. They're all set globally. Okay, so block size, that's the size in pixels of your matching filter that you're trying to match the point. Okay. Uh, there's a bunch of other things in here. Let's see. Minimum disparity. Yeah, I've got it set to 0. Okay, so for a zero disparity, the thing is at a far range. It's at an infinite range. So if you only have a small range of interest, you can set the minimum and then the number of disparities, and that will cap the range on each end. Um, but I'll let you go through the documentation and you can figure out what these things are. I just use the nominal values that they suggest for most of them, but they're all tuning coefficients. Okay, so this is the block match algorithm. I didn't bother to try and super tune it, but you can see here's that white spot from the arm that's sticking out closest to the camera. These are a little further away, a little further away, a little further. This is basically background, and some of these are slightly different um, tones of gray. You can see that here and here it's slightly different. This is being closer. Okay. So what I did is I actually went in and uh, used one of the feature finding routines to find a set of points. And you'll notice that these are over here, and that's because they're basically out of view of the stereo image. And you can see the rest of the points scattered around the image in here. And most of them are on more interesting points. Okay, so this is the same thing, only this is the semi-global block matching, and you can see that it's almost the same image. Like I say, I didn't tune these to get the best images, but yeah, that's kind of what it is. And why you see like dark spaces over here, and that's because the left camera, which is this is relative to, can see back there, but the right camera can't because it's being blocked by this structure here. Okay. So, this is not a great stereo image, but it works. Okay, wait a minute. Why compute the depth for all of the pixels in the image? Like about 1 million, right? I don't need that. All I'm interested in is the depth of our point set. So if we pick a set of points that's 100 pixels, why do 1 million? Unfortunately, the stereo algorithms do not have a mask, and so they don't allow you to do just certain pixels. They do the whole image. Anyway, okay, so what we can do is we can actually match points that are on the same line, and we can do it for, we can pick our set of points that we want to match and do just those. Uh, some things that you have to watch for or look out for when you're doing that, if you want to do just the points, the few points rather than the entire image. Disparity has to be positive. Anything in the right image is going to be positive with respect to the left image. So if you do calculate something that where the disparity is negative, that point is behind the camera and you don't want to use it in the rest of the processing. So you can eliminate potential matches very rapidly just by looking at the difference between the point positions. If the distance in the V direction, vertical, is less than a certain amount, then the points are approximately on the same line. So that's a good choice of a matching point. And you have a maximum disparity, which is going to be greater than the point difference along the x-axis, which is going to be greater than 0. Okay, so these give you some clues to throw out most of the points when you're doing matching. So it's much faster than doing all the possible matches. So you're just now matching 100 pixels compared to 1 million. And why is that important? Because the stereo matching is a very slow algorithm. It takes time. Or you can do the full disparity calculation the way the OpenCV does, but only on a certain point set. But you're going to have to write the software to do that. Or maybe find somebody that's written some software to do that. Going back to that. So this is what I'm planning to do. I haven't had a chance to do it yet. So I just calculated the full stereo image and used that. But this will make it much faster until you'll be able to keep up with the motion of the robot. Okay, so now we've done the image sequence and we've found the range for our set of interesting points. So now we're going to do a feature detection. Actually, you probably want to do that before you do the stereo. So what are feature points? Okay, we want to be able to match features in two or more images to estimate how the camera is moved. So we want to be able to find a set of feature points in the first image and again find those in the second image and then match them. Okay, and that is really the key to how well you can make this uh, visual odometry work, is how well you can match the points. So the features should be able to be matched in the successive images. You want to be able to take care of image rotation, scale changes, and changes in illumination. So we talked about the changes in illumination before, and we took care of that with just doing the image normalization. But we still have some problems if the image rotates very much, if the camera rotates, or if it moves quite a ways with respect to what it's looking at. Then you have some scale changes and rotation changes, and a lot of the matching algorithms don't do well with that. Okay, finding feature points. So there's a whole bunch of features. This just lists a few. OpenCV, I think, has a dozen or more, some of which are better than others. Okay, so so how do some of these algorithms do? So you can repeatability, localization accuracy, robustness, and efficiency. All right. So things like the Harris and the Shitomasi, which are very similar, are very efficient, but um, not real good at the robustness in terms of rotation and scale invariance. Okay. So you can come down here to the SIFT features, which are very good at the robustness, the rotation, and the scale invariance, but they're not very efficient. They're very slow. And then there's a bunch of others. So SURF is a takeoff of SIFT, which is quite a bit faster, but doesn't do quite as good a job. Okay. The thing to know about SIFT when it first came out, it was patented. And so you couldn't just go and use it on a commercial product without paying the owner. The patent is not run out, so it's freely available for anybody to use. Okay, Harris detector, which was at the top of the list. So this is the math of how you do it. You basically compute a factor R, okay, the determinant of this matrix minus the trace, a factor of the trace of the matrix. Okay, so when the absolute value of R is small, the region is flat. So that's not a point that you want to use. When R is less than zero, which happens when either one of the eigenvalues is high, but not both, then the region is an edge. Okay, well, we really like to have corners rather than edges. So when R is large, what happens when you get both of them large and they're about the same, the region is a corner. Okay, so this kind of shows that. So eigenvector, lambda 1, lambda 2, this being the larger one, this being the smaller. And you can see points here in the green area are the ones that you want, where both lambda 1 and lambda 2, both eigenvalues are large and approximately the same. So those are the ones that you want to use.
Is that sort of like finding contrast, but in 3D as opposed to 2D?
No,
Or
this is still 2D. There's only
okay.
two dimensions here, X and Y. Um, and
Oh,
yes, it's
is
like
the point? It's a
finding,
point where the line changes its angle. Is that the
yes,
idea?
yes,
Okay. All right. All
yeah,
right. So this is like where a wall joins, but then there's also that line at the floor, for
yes,
example. Okay.
yeah. Both of those would make good points.
Okay. I see.
Okay, so we've got key points, but now we have to have descriptors because we're going to match them, right? So we have to know how to describe one so that we can match that description with the point in the other image. Okay, so often key point descriptors done using the Harris or the Shitamase operator or some of the others, it's often just a patch of the image around the key point, and you can vary the size to get better or worse matching. Okay. Works okay with translation. Unfortunately, that descriptor doesn't work so well with scale changes and rotation changes. Okay. If your rotation is not too bad, it will work. If the patch is relatively small, scale changes have a problem with it. All right. Lots of other point descriptors. I've invented a couple and used them, and they work. Harris is a very good one, I find anyway. So here's an example of a Harris detector. And you can see the red dots, which it detected as interesting points. Here on just a straight chessboard and here on a distorted one. Here's the image, and you can see the green points on a lot of the key points here. You will also find some green points that are a little harder to see, but you kind of wonder why it picked that one and these two and some of those. But okay, that's fine, as long as you can pick the same points in the next image. Okay, the SIFT detector stands for Scale Invariant Feature Transform. And it's a feature detector that will look for points which are invariant to scale and rotation changes. And it does that using a difference of Gaussians over multiple scales, and then it finds the extrema, the max and min points across those uh, Gaussians and a difference of Gaussians. So the descriptors are not just a patch now around the point that you pick, but they create a set of orientation histograms of 4x4 blocks that are around the key point. And it leads to much better matching in the case of rotation. And also scale, because now you're looking at orientation rather than actual distance between the pixels. Very complex to compute, so it tends to be slow. And let's see here. The unfortunate thing is it's complex and tends to be slow to compute, but it usually produces the best set of key points and descriptors that you can get. I've seen a number of papers that talk about different key point detectors and their descriptors, and SIFT usually is, if not the best, it's one of the top best of those. So it's one that you can usually rely on. It just takes a lot of computation. Okay, difference of gradients and scales. So you take your images and you pass them through a Gaussian filter of different um, widths. So this one might have a variance of, say, 2 pixels. This one might be 4. don't remember the exact numbers that they use in here. They then take the difference between the two Gaussian filtered images and create a difference of Gaussian image. And you see that. So this would be the difference between, say, a 2 and maybe a 3. And this one would be the difference between 3 and 4, or whatever the ratio of the Gaussians is. And then you go to another scale. So
and do it all again. So
and
this is why this takes so long, is because you're doing all of these parallel every pixel operations over and over and over and over again, right?
right.
So the question I have is there like a version of this that runs on a GPU that's like super fast? Does OpenCV not use the GPU, or is it just still super expensive even when it's run on the GPU?
They do have many of the algorithms coded up in CUDA for GPUs. And I think this may be one, but I'm not positive. I haven't dug into it enough to find out. But yes, I'm sure people have done this on GPUs. Okay, so this is an idea of what some of the SIFT points will look like. And you see some small ones, and then you see some larger ones and some larger, and they don't appear to be on corners or things like that. But they're image patches that are maybe consistent and the size is consistent. And so you get that information in the descriptors. Okay. So you can see them all over here. But they tend to be some of the best descriptors. Okay, so fast is another one, and this one is very fast to compute. And basically, you pick a point in the image that has in some intensity IP. Okay, consider a circle of 16 pixels around it. So, kind of in a circle around it. Okay, so you designate P as a corner if there are some number, in this case 12, contiguous pixels that are brighter than IP plus some threshold, which you set, or all darker than the image point minus some threshold, which you set. Okay. So as you can see, there's not much computation here. It's pretty fast. To give you a better idea, so here's P. Here are the 16 pixels around here. And you start at 1, that's smaller, 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 smaller. Now you're getting into the same smaller, smaller, smaller. So that would be detected as an image point. And you can see where on the image it actually appears. So this is an example of what you get. Okay. So there's two techniques here, and we'll talk about this one without non-max suppression. So this is just doing exactly what I did before, or what the description was, picking P. And then you get all of these points. And so like on this point here, you might find you get 2 or 3 detections on it. Same here. Okay, so non-maximum suppression being added to that, it says that if I pick a pixel that I create as a image point, that a feature point that I want to use, then I won't allow anything else that's within a certain distance of that to be picked as a pixel. Okay, so I pick the best one, the one that's got the best result here. And you can see the points have been reduced. I don't think he did a good enough job of non-maximum suppression here. And you can see things that are on the lines, on the edges, rather than corners, and things like that. So, yes, it's very fast. It's probably not as good in terms of picking points that you can track to another image. Okay, so here's some of the OpenCV feature detectors that you can just use: Harris, She, Tomasi, SIFT. Surf is a speeded up version of the SIFT features, and it's not as good. Fast, we just did. So brief, binary, robust, independent, elementary features, orb, oriented, fast, and rotated, brief. Since SIFT was originally patented and OpenCV wanted to have something that was close to good, they invented their own, which is the orb. And it tends to be pretty good. So brisk, binary, robust, invariant, scalable key points. And you can go look those up, and there's lots of information which will tell you how to compute them and exactly what they are. There are some more that are available to OpenSea, but they're in the submitted category. People submitted them. They're not in the main OpenCV set. Okay, so now we've got key points, and we need to match them in successive images. So we use the descriptors. Okay, so we have a descriptor for a key point, and we do a correlation matching to find that same feature point in the next image. So we've actually done key points in both images, and now we're just trying to match them up so that we have this correlation between one point and the next image. So there's two functions in OpenCV that will do that. One is brute force matcher. So it takes the descriptors and uses the sum of the squared distances. Or differences, I guess is what to say. So the smaller the number, the better it matches. They also have what they call a FLAN matcher, fast library for approximate nearest neighbors. In both of these, you can get more than just one match. So you can get a set of 2, 3, 4, 5 of the top matches. And so if the first one doesn't work, maybe you want to use the second one. And so this is an image where they've shown the lines that match. So the green lines actually are good matches and the red ones are not. Matter of fact, you can see this one goes all the way across. So there's an edge up here and there's an edge of about the same kind of thing down here because it's just a point, a small patch around there. All right. And so they got that matched. So that presents a problem because not all of the points that you get matched are actually good points to have matched. And they're going to throw off your answer for translation and rotation of the cameras. Okay, another point that you might have a problem with in one image, a point can match to multiple points in the second image, and it's the picket fence problem. So here, one point, one picket can match several different points in the second image. And so that tends to be a problem, and that will throw off your answer quite a bit.
So
So
can you just throw those away? Like if
yes,
you get a ton of matches, you just toss them. Okay.
yeah, and we'll and we'll talk about that. Okay, the next problem with it is independent object motion. Okay, so here's a bunch of cars moving down a runway. Here's the cars moving down the runway a few frames later. And so the difference between here and here, that's what you want to know, but not necessarily the distance between here and here. Okay. Yes, these points will match absolutely beautifully because they're high contrast points. But you have to be careful not to use them because they're not going to be consistent with the rest of the scene. And we'll talk about how to get rid of those. Okay. So what you want to do with all of those points is you want to create an essential matrix. You want to estimate the essential matrix, which is a 3x3 matrix that relates the corresponding points in multiple images where the cameras satisfy the pinhole camera model. So pinhole camera model, no distortion. So that's why we did the undistort at the beginning. We have to do the undistort anyway to do the stereo, and so we just carry it along here and everything's fine. Okay, definition of the essential matrix. This is the points in the second image, okay? And this is the points in the first image. And so when you do this multiplication, it should all come out to be 0. And so what we want to find is this thing in the middle. So there's a lot of techniques to do that. The other nice thing about the essential matrix is that it's basically equal to this slightly strange version of the translation times the rotation matrix. And so you can extract both the rotation and translation out of the essential matrix. And that's the answer you want. How far did I move and how far did I turn?
Just to make sure that I'm getting this, what we're looking for here, the essential matrix is there's one matrix which represents the translation and rotation, a single transformation and rotation that we apply to all the points that makes them all then work together. Is that what we're looking for? Or the one that
Correct.
does the best job of it? Okay.
Yeah, yeah. We're looking for the one that models the entire image translation rotation problem. And that works because we have um, linear images rather than the distorted images. Now, you can do the same thing with the distorted image, and at that point, it becomes called the fundamental matrix. Okay, and you'll see a lot of stuff in the literature about fundamental matrix and essential matrix.
But at that point, you're not doing just like standard translation rotation type
Yeah,
transformations, right? Okay,
right. Yeah. So this is what you want, the essential matrix.
got it.
So the question is, how do we build the essential matrix? This is not a real obvious equation just to go solve, all right? And then how do we extract translation and rotation out of that essential matrix? So those are the two problems that we have left. So there is a caveat here. We estimate the um, essential matrix using a set of matched points. And if those points don't work very well, if there are errors between the matched point sets, either the match wasn't right or they're not consistent with the overall image, like we saw in that picture of the matched points, then the essential matrix is going to have errors in it, and the rotation translation is going to have errors in it, and so we get errors in our odometry. So we have to have some way to get rid of those. Have to recognize the outliers, which are the ones that aren't consistent with the larger set, and throw them out. And so typically what's done is we use a technique called robust statistics. Okay. And one of those is RANSAC, which stands for random. Uh, I guess we'll have to I don't remember. So we'll have to get to the next couple of slides and it'll tell us. Okay. So the solution to the essential matrix. So you got Y as one set of points. Okay, so this would be the horizontal direction, vertical direction, and Y prime, which is the second set of points in the other image, Y horizontal, vertical. The one here just makes them what we call homogeneous equations or homogeneous vectors, and it's very useful in doing the computation. The essential matrix is just a 3 by 3 matrix, and you can see we've labeled all of the elements. Okay, so what you do is you multiply all of this out to get to equal to 0, and you get this equation, and 1, 2, 3, 4, 5, 6, 7, 8, 9 values, right? In the equation. And so you can create two other matrices or vectors, okay? E times Y equals 0. Where Y looks like this vector for one set of points, and E looks like the elements in the essential matrix. Okay. And so what you see here is this Y hat is basically the vector representation of the 3 by 3 matrix of the second set of points times the first set of points transposed. So we're stretching them out and making them into vectors and then doing the multiply, and this is what we get. Okay, so that's one point. And so we've got nine unknowns here, and so you would think, yeah, well, we need nine sets of points there to solve that set of equations, right? We don't know what the e's are, and we do know what this is. The interesting thing is because there's this one down here that the essential matrix is a singular matrix. And so you can't use just some of the standard techniques to solve it. Okay. Which would be a matrix inverse. So what we do is we create a matrix of all the matched point vectors. So rather than have this linear equations, we just stack them up. And so we create a matrix. Then we use a least squares solution to solve for E. And what you really need to do is a singular value decomposition here because the matrix is singular. And so that you have to use the SV to do that. So then you can, once you've got that, you've solved for E, then you can reorder it back to the 3x3 matrix. And that's basically what you do. Okay. And here we're going to talk about Ransack and the 8-point algorithm. There's lots of algorithms. Wait a minute here. There's lots of algorithms to do all of this and to actually solve for this E vector or essential matrix. One of them uses the SVD. There's several others, almost too many to count. But we're going to use what's called Ransack and the 8-point algorithm. So the 8-point algorithm has a couple of key features here, and it's very important that you do this. So you normalize all of the data to a zero mean and a variance of 2. Why do you have to do that? Well, if you use the values of the pixels, like 600 pixels or 300 pixels from the origin of the image, when you create this vector, you find you get some very large numbers and you get some very small numbers when you're trying to solve it. And so the condition of the matrix is it's ill-conditioned. It's not very good. And so trying to solve it with all those large numbers and all the small numbers together, it's like trying to subtract two large numbers and get a small number and then use the small number. And so it's the resolution of your arithmetic. And it tends to be a very difficult problem. So what we do is we normalize everything to a zero mean and a variance of 2. So you just take all the data, compute the mean and variance of the image data points that you're interested in, and then change it so it has a zero mean and a variance. But you have to keep track of the factors that you use to produce the mean and variance. All right. A little bit confusing, but all right. So it improves the condition of the matrix and makes it much more solvable. Ransack is a robust statistical technique that removes the outliers from the data. Okay, so we saw points that matched, but they weren't consistent with the rest of the points in the image. And so Ransack is a way to throw those out. So it improves the model accuracy for the essential matrix. Okay. Here we go. Random sample consensus, Ransack, is an iterative method to estimate the parameters of the mathematical from a set of observed data that obtains outliers. So if this is your initial set and you're trying to figure out what the line is here, and the line is defined by two numbers, slope and offset, right? Well, if you start keeping these in here, that line could be almost any place. But once you fit it with Ransack, it throws out all of these outliers and uses only the inliers along the line here to compute the values of the matrix. Okay. Here's some pseudocode for what it does, and I'll go through this kind of quickly. So while iterations is less than some number, it's an iterative process to do this. So you do it some number of times. So select maybe inliers is none, which is a randomly selected set of values from the data. So instead of using all of the points in the data, in our case, we're using the 8-point algorithm. We use 8 points. Okay, randomly selected, which means you can't have your random selection process produce the same number for any of those points. So then you have a maybe model. So you create the essential model fitted to those maybe inlier points. So that was doing that calculation with the vectors of the new and old points. So you set the confirmed inliers to an empty set, and then for every point in the data, you fit that point using the model, and you find all of the points that are in the data. This is the whole set of data now that have an error smaller than some threshold that you select. And if it does, then you add the point to the inliers. And you go through all of the points.
And I would assume that you toss some other point out, or is it you just start with 8 and then it grows over time?
Yeah. So this is the thing that tosses them out. All right. So you start with all of the points, you compute E, and then you
Narrow
go
it down.
back and yeah, and then you go back and see if the Y and the Y prime produce a value of the Y prime essential matrix E times Y is equal to 0.
Got
Okay.
it.
So that's your error calculation. And then if it's less than a certain threshold, you keep them. If it's greater than the threshold, you throw them out. They're not consistent with the data set. Okay. But the data set that you're using to calculate the E here is just 8 points. Okay. And then you go through and find out how many confirmed inliers is in that set. And in that set. And if it's greater than D, then it's probably good. Another threshold that you have to set. So then you look for better models. So you look for model parameters that fit all of the points in the confirmed inliers. And this is the measure of the error of how well the better model fits all of the points. And you do this for K, the number of iterations, and find the best model. Okay, the best fit, the smallest error. And that's the set of points that you use to actually build E. So it's 8 points now because you've gone through a K sets of 8 points randomly selected from the total data set, and you've computed the essential error and found out which of those models produces the smallest amount of error. Does that make any sense? Okay.
Yep, I'm getting it. I get the feeling that you might enjoy the math a little bit more than most people, Bob.
I do.
I'm hanging by a thread, but I'm getting it.
Okay. The nice thing is there's a shortcut. So find essential matrix. OpenCV has that nice function in there. Points, first set of points, second set of points. The camera matrix, which is basically the intrinsic parameters of the camera. Ransack, there's half a dozen different things that you can select here. If you select Ransack, you get the 8-point algorithm. There's a 5-point algorithm. There's a couple versions of a 7-point algorithm. And then there's another version of the robust statistics, which I think is LMED or something like that. These are a couple of factors that are associated with Ransack. And then it also produces an inlier matrix. So You've got all of the points. You've got them listed 0 through n. And the inlier matrix puts a 1 in the case of where that point is an inlier for the essential matrix that you've computed. If it's an outlier, it throws it out. And you need that a little bit later here. Okay. Okay, now finding R and T. So E equals this T matrix times the rotation matrix. So you do a singular value decomposition of this and you get something that looks like this. U sigma V transpose. So U and V are 3 by 3 matrix, and sigma is the 3 by 3 diagonal matrix, and it looks like this. The interesting thing is here that one of the rows is all 0, so that says it's a singular matrix. So the eigenvalues, the other two eigenvalues, are actually equal or should be close. So this is an indication of how well your calculation did. Okay. So R, then you use U, V times and a W in here, and W looks like this. Okay. The T looks like U, Z, and here's Z. So that's the calculation that's actually going on. So there's quite a bit of math and actual calculation going on behind the scenes here. Oh, shortcut. Recover pose. Okay, essential matrix, points 1, 2, camera matrix. You get back the R and T. Okay?
We're vicariously enjoying your enjoyment of math.
I put it in there just to let you know that there really is something behind all of this, and it gives you an idea of how much computation has to be done. So it is important. Okay, so the essential matrix is singular. Ooh, tends to be a problem in most mathematics. Only valid up to an arbitrary scale. Ooh, what does that mean? So T is only valid up to an arbitrary scale. So damn it, the thing that we wanted, which was T, is only valid up to an arbitrary scale, and this is not useful to us. So help. Well, we can go back to the original data. We do have R, which is valid. And we can use that then to go back to the original data with R and compute T. And it looks like this. So T is the second set of points minus the rotation matrix times the first set of points. So we're taking the first image, we're rotating it by R, okay, and then we're subtracting it from the second image. What's left? T, the translation. Okay. So X1, X2 are the object points, but what we have is image points. So we need to actually produce where the object points are in the real world. So U, which is the image point, focal distance times the X position of the thing divided by the depth, the Z axis, okay, plus U0. So U0 is usually the lower left-hand corner of the image. Excuse me, we want the center. And so U0 is in the center. So it's usually like in a 1280 by 720 image, it would be 643 and 320 for the U0, V0. Okay, so you convert that, compute X and Y. Z comes from the stereo. Okay, focal distance times the distance of the baseline. This is the distance between the camera in your stereo setup, okay, divided by this disparity that you compute from the stereo image. Okay, so what we do is we compute T for all the inliers, and then we take an average. Okay, so here's an example. What I did is I created a set of points, arbitrary points, in the image, then used that to create my essential matrix, and then extracted RNT out of that, and then use that. Okay, so it's kind of instructive to take a look at the code and then the results that you get. So the first camera, this is the translation and rotation matrix for the first camera. Well, it's 0, right? That's our reference. We're interested in where the second camera is relative to that reference. So in the second camera here, I gave it a rotation around the x-axis of 20 degrees. This is in radians. It's equivalent to 20 degrees. Okay. Oh, excuse me. Yes, right. And then there's this, what you really want to do.
Isn't that a translate? So wait, why are you doing a rotation on the second camera? I thought you wanted to do a translation on the second. Oh, I see. You get down to that, but you did a rotation here just to show off, or was there a reason for
No,
doing?
because if you're moving, you can't guarantee that the camera has the same rotation.
Okay.
Right. Your robot may have a slight tilt to it, or it.
Oh, so this is the ability to handle the fact that like the robot is rolling over a plane or
Yes.
something. I got it.
Yes.
Okay.
Right.
And this
Okay.
is something you would get from, like, for example, an IMU, or you would get it from some other source of information.
You could. Yes.
Okay.
All right. We're actually going to calculate it. Okay. But this is a vector, so this camera rotation vector, and what we really need is a camera rotation matrix, which looks like this. And you'll notice since it's around the x-axis only has the unit component in the first value. This is actually the sine of 20 degrees and the cosine of 20 degrees. No, I got that backwards. The 0.939 is the cosine, and the 0.342 is the sine. Okay, so how do you get from the rotation vector of saying I want 20 degrees rotation to the rotation matrix? Well, there's a whole set of calculations you can do, or you can use this little thing down here. Where is it? Fourth line down on the second set of code says Rodriguez. And Mr. Rodriguez came out with a method of going from rotation vector to rotation matrix, which is actually quite simple. But the other thing he did is came out with a scheme to go from rotation matrix back to rotation vector. And we use that at the end. Okay. So that's what these matrices would actually look like, or should look like at the end when we get done with all of this. Okay, so the camera intrinsic matrix is just like you might suspect. This is the focal distance, center of the X direction, center in the Y direction, and number of pixels. Okay, so I used a random number generator to compute position of a whole bunch of, let's see, 100 points. Okay, and then I used the camera, the rotation translation matrix that I computed before to compute the second set of points. So this is the first set. Here's the second set. Okay, interesting to note. So the translation of the second set was 100. So
Wait a minute. Hold on a second, Bob. You're building up test data? Is this what you're doing? Oh, yes. I totally missed that. Okay.
Okay.
So you're building up test data to then run into the actual system. I got it.
Yes. Yep. Okay. So the interesting thing, if you look on the point array, this is minus 341 in the X direction, right? We translated it by 100 units, so it's minus 241 over here. Well, because that we've done that, and we've also done some rotation, the third and fourth, second and third values are different. But you can always count on that first value always being 100 greater than the second value. Okay, so we did that. We then did, in the code here, project points. We basically projected them onto the image plane. And so we took the rotation and translation vectors with the camera matrix, and we created a set of points. We did that for both images, and this is the points for the first image. Down here, we can do the essential matrix computation and look at the errors also. Here's the essential matrix. It's interesting to note that this 0, 0, 0, 0, 0, and the only 4 values that count are down here in the lower right-hand corner. All right.
And
So
when you say
kind of,
0, you're talking about e to the minus 07. That's
yeah,
effectively 0.
correct. And this is the position of the actual points in the image. So they go up to well over 1,000, and here's one down at at 7. Can't have any negative numbers in here. Won't work that way. All right. So then I went and took that essential matrix that we calculated using the image points and calculated what the rotation translation is. And you can see, so here's that displacement vector, and the first 2 elements are identical, and the third one is 0. So that's a singular matrix. Okay, U, V, and you get the rotation matrix. Okay, 1, 0, 0, 0, 0. And these are the same numbers that we used in creating the essential matrix in the first place, or set of points, right? So we take the Rodriguez algorithm, which can go either way, and it's over here. And we calculate the rotation vector, 20 degrees, which is what we set. And then we go calculate the translation vector that you get out of the essential matrix. And lo and behold, it's minus 1, 1. Doesn't do us a whole lot of good. So we have to go back and calculate that translation vector. PA is the first set of points. We rotate it. We do this by row because that's each of the vectors. And then we compute the translation by subtracting the second set from the first set of points rotated. Okay? And then we all add them all up, take an average, and it looks like pretty close to 100, 0, 0, which is what we set. So that's all kind of interesting.
So at that point, you know that your code is probably going to work on real images.
Yeah, yeah. The interesting thing about it, though, is we started with some fixed points that we knew because we generated them, and then we calculated back and we found out that the rotation and translation is exactly what we set within some small amount of error. Okay, so how could this thing possibly have errors? It's the point matching. If you don't get the points accurately matched, or they're inconsistent with the majority of the data, then you're going to get errors. So all of the work that you really have to do is making sure that you've got good images, you've done a good job on the stereo, and you've done a good job picking points and matching them.
And there's a certain amount of error that's inherent in the size of the pixels on the image anyway.
Correct.
Right?
Yes.
Because the center line of the pixel may not, what's the word I'm looking for here? Like it can only align with the pixel in the other side to the degree that the pixel is small.
Yes.
That's not a very well said thing, but I think yeah.
Yeah. So I'm going to come down here. Okay. So this is the Harris detector, right? And how you get it. And it's only good to a pixel.
Right.
Because you do it a pixel at a time. What you can do, and there is a function in OpenCV which says interpolate. And so you can interpolate this, given the pixels around it, or the magnitude of the detector for the pixels around it, to get a fractional number, which is going to be more accurate.
It's aliasing in reverse.
Yes. Right. So you're doing an interpolation, lots of ways to do the interpolation. OpenCV has one or two that they use, and that's what you need to use for this. Otherwise, you're limited by the pixel size or the resolution of the images.
Cool.
Okay. It doesn't really help in terms of the range because the range calculation is disparity. And so you're using the best match. And yeah, the disparity calculation is subpixel calculation, but it's still has problems with it.
So does that mean then that this works better for calculating how much your robot has rotated or translated left to right, but it doesn't necessarily work as well for how far forward or back your robot has moved? And if that's the case, then would it be better to have your camera pointed off to the side instead of directly along the robot's usual direction of motion?
Yes. Whoops. Let's see, where am I? Okay. Yes, that's exactly true. Wait a minute. There we go. It's exactly true. And the reason is because the range calculations are not terribly good.
Yeah, right. Yeah.
So if you have shorter range and you can match the points, yes. So points on if you're looking exactly where you're going, so points on the outside of the image will tend to be better. And so that's where you get in the weighting for the range directions. You weight those calculations a little bit less.
I got it. Oh, okay. Oh, that's
So it's
interesting. So even if your camera's pointed straight ahead, you are still getting data off to the side that gives you a better idea of how far. And that just makes
yes,
sense,
yeah,
right? That just makes perfect sense because those are the pixels that are going to change the most as you move forward.
correct.
You watch I'm demonstrating that effect,
Yep,
right? Yeah.
yep, yeah. So that's exactly it. So the keys are which points do you use, how well you match them. Even if they're well matched, then you have to go through something like Ransack to throw them out because they may not be consistent. Okay. So the calculation of the essential matrix once you've got the points and the calculation of rotation translation out of the essential matrix, that's just plain numbers, right? And the calculations are accurate. So it depends. The whole thing falls down to those match points and how well they're matched. So that's your, how do I get better performance? Match the points better. Okay. So we've gone through, we did the pose change from one image to another, got translation. So we know how far and in which direction we've moved because we got X, Y, Z. Rotation, and we know what the pointing direction of the camera is in the three orientations possible. So you got an XYZ rotation, and you know what that is. So if you want to know what the motion track is, you just concatenate them, kind of like you do with your wheel odometer. So you measure how far you've gone between each time you take a sample and add it to the next one. So it's very, very simple. Okay. A little bit of some performance pictures, not a whole lot. This is a set, and I won't give you the names, of 4 different commercial um, uh, visual odometry systems and how accurate they are. And so you can see the track. They start here, go up here, go here, and then come back. And that's why you can see double lines. Okay. The 2 that work pretty well are the red one and the green one. The other 2, well, they kind of go off a little bit. So this is just a 2 turns, and this one is a little bit more complicated, but they start here, go this way, and you can see again the red and the green ones do a little bit better. So it has to do, again, with how well you match the points. The image on the left over here is kind of interesting. So the actual track is closer to the red one. Not real great. But the blue one, that's before removing the outliers. So the red one is after doing ransack, and the blue one is not doing ransack. So you definitely want to have the outlier removal in there. Okay? And then this is the same one that we saw earlier. I somehow have to get that over there. Ah,
Is it not letting you show the last slide because?
yeah, because I don't know what I'm doing, basically.
Yeah. We reach a point where the specialization of knowledge becomes an issue.
I'll just do it this way. Can you see that?
Yeah.
Yeah. So this is one where they've got the algorithm working pretty well. And so it tracks.
The critical point here, Bob, is where's the link to the presentation? Where's the link to your sample code? And how much do you charge next time I have to build something like
The sample code is all in the presentation, so I'll send it all to Steve, and when he posts it, it'll be up.
Okay.
Right.
Yep.
Awesome. Absolutely awesome. Way too much math, but it is valuable still to understand.
Yeah, but it's the math that makes it work. And it's helpful to have an idea that there is something really behind it.
Right. Right. Yeah. That's it. The other thing that's kind of amazing to me too is that we're at a point now where we can actually do this kind of compute sort of in real time, right? Like this guy is obviously doing this. Well, I mean, maybe he's recording videos. So who did the actual Andrew Comport, I guess, did this this particular test? I suppose you could do that from not in real time, but the point is you can do it in real time these days, especially with using like GPUs or FPGAs or something.
Yeah, so the two big computation things here are if you're using SIFT for the point detector and matcher, that's going to take a lot of time. And the other one is the stereo calculation. So if you use OpenCV stereo, it does the stereo on the entire image, but you only want 100 points or so.
Right.
So if you can build some code or find some code that just does it on a particular point, that's going to be much faster, much faster.
And so on that, wouldn't it be possible to do just hand OpenCV a strip across those two images, and then as a separate operation, hand it another strip, and then as a separate operation, hand it another strip? You know, maybe only 10 pixels high or something like that.
That's possible, yeah.
Yeah, and then I don't somehow combine all of that information back together again.
Yeah.
And then the other question I have too is there probably isn't a way of doing this, but if the information, well, no, because you do want to understand if you've translated left to right. I was going to say, what about just cutting out the center of the image? If that's not going to give you good, information, but you still want to be able to get the translations left to right, and you want to be able to get your rotation. That's really important, and that those pixels would contribute to that. So you don't want to remove them.
Yeah.
Yeah. Cool. I'm going to let this all percolate into my head, and I'm going to be smarter once I actually understand it better.
Yeah, so the real key factors here as to how well you can make it work are how well you can match the points and how well you can get rid of outliers.
Right.
Point matches that are not consistent with the rest of the matrix.
because something was moving, or because they're
You got the picket fence problem, or yeah,
yeah, that
yeah.
kind of stuff. Right. Awesome presentation, Bob. Really appreciate it. That's
Well,
I
thank you.
understand a lot better.
Yeah. Thank you, Bob.
And so you can do this real time. So you can put it on your robot and just have it go driving along. One of the keys is you don't want to do it frame rate because there's not enough distance translated frame to frame. And so it's mostly going to be noise. So you want to take a picture, wait a little bit, take another picture, wait a little bit. And so that depends on what your robot motion is or what you expect it to be.
So if you, let's see, you want to do something where you wait until you change direction. So like if you're going forward for a certain period of time and then you're going to rotate, if that's your motion plan for the robot, right? You want to, maybe hit it once at the beginning of the forward motion, once at the end of the forward motion, once at the end of the rotation, once at the, after you've done the next translation forward. Is that what you're talking about? Like try to match it to the motions?
Well, you can do that, but remember that as you don't want to do it frame rate because the motion is too small.
Well, right.
The motion can't be too big because you're matching points from one image to the other so that the camera has to be able to see the same thing. Yeah.
Right. So you would put like an upper limit on it, like do it every, X amount of expected motion.
Yeah. So if your velocity is 1 meter per second, maybe you want to do it 3 or 4 times per second.
Okay. Right. Yeah. And that's based on like what you're driving. So, I mean, you don't have to have like wheel odometry on top of whatever you did. This is just to give it an expectation.
Yeah. So if you set your velocity to tell it to go forward at, like I say, 1 meter per second, then you can say, okay, I want to do it 4 times in there. I want to do something that's like maybe 10 inches to a foot apart.
Bob, I'm loving the hell out of this, but I got to take this phone call, so
okay.
I'm gonna run. You guys, awesome meeting. Talk.
Yeah.
Anybody got any other questions?
Looks like you got them all.
Okay.
All right. Well, thank you so much, Bob. Just generate a PDF file of your presentation and send that to me.
Okay.
Yeah, and that's what I post. It's a little more compact than the PowerPoint. So.
Yeah, the PowerPoint I think is almost 7 megabytes.
Yeah. It's PDF probably come in at under half of that. And all right. Well, I'm glad we finally got you to do this. I mean, this I know it's been a long time, but
yeah, my plan is to actually get the thing built and get my robot put back together. I broke it. And so, being an engineer, you're trying to fix something and, I could do that better, right? So you redesign it in the process. So it's taken a long time to get it put back together.
Yeah, I know how that is. Yeah. You gotta kind of got to move, but you got to move past that analysis paralysis thing, and get to the point where you're actually making some progress.
Yeah.
Yeah. All right. Well, we got a few stragglers here yet, so thank you guys for hanging in there. I know this went a little bit long, but hey, it was great presentation, and it's a broad topic, so you did a great job. Thank you so much.
I'll try to fill you in on when I get it actually built and operating, and you can see how it works.
Yeah, I love that. All right. Well, since we've gone fairly long here, I think we're just going to go ahead and call the meeting. And thank you guys for showing up. And this will probably sometime in the next week or so. I'll try to get this up. I mean, we got a busy week coming, so we'll see. So I'll try to get it posted soon. So, all right, have a good one, everybody.